I was talking about how to ascertain what should be R2 tensor when we are trying to write an equation of how the amount of an entity changes in that control volume. I was saying that you imagine for a moment that the background velocity field has been switched off, which is V0. I wrote that mistakenly as V not equal to 0 yesterday. Imagine V is 0. And then think about what other reason can change this n tensor. Whatever reasons come to your mind, I mean in a reasonable manner, not in a random manner, guided by appropriate axioms and laws, those reasons would go and fit in that placeholder R2. Okay, and that guidance should come from relevant laws and axioms. I was talking about the entity mass. If the entity is mass, then the guidance of how to ascertain this R2 tensor comes from the law of conservation of mass. For a moment you think that V has been shut off. You have a certain amount of mass contained inside this. Why would it change? It cannot change because mass can neither be created nor be destroyed, and thus R2 for the entity being mass will be equal to 0. Now here you may have a doubt in your mind. I hear this doubt every time I teach at around this time of the course, that when I close my eyes and try to imagine V is 0, I visualize that the temperature is increasing, and thus the fluid will expand. And as the fluid expands, some fluid can spill out of that control volume, or the temperature goes down, the fluid contracts, and some fluid from outside pours inside the control volume. How am I accounting for that? Shouldn't I account that using R2? The answer to that question is R2 is not about that kind of expansion and contraction. If the temperature rises and the fluid expands and it spills out of the transparent control volume, that is still advective flux. If it is spilling out, it is spilling out with some velocity on the surface of the control volume. Imagine a fluid expanding. So this is the control surface. The fluid is expanding. As it expands, it spills out. But when it spills out, it must be having some velocity. The fluid that has already been taken into account. Where? In R1. So expansion and spilling out is still advective flux. That's why that expansion contraction effect need not be counted in R2. R2 is non-advective flux. And as I'm saying, non-advective flux is 0 as far as mass is concerned. In classical mechanics, again in nuclear reactions, energy will be converted to mass, then this will not be 0, but in our class we are only focusing on classical mechanics. Then I was talking about this bacteria population. If the entity is bacteria population and you have to think about what R2 is, R2 will be the net rate at which the population of the bacteria increases per unit volume of the fluid. Okay, that will be some model which you will get from a biologist, and that has to be put there. All right. When it is fluid momentum, when the entity is fluid momentum, close your eyes, switch off the velocity field. Why would the momentum of the chunk of mass that is right now inside it, there is some mass inside it, you have switched off the velocity field. Why would the momentum increase? The momentum would increase because there may be some external forces acting on what? On the mass that is contained inside the control volume. That's what I have written here. R2 should be the net external force that acts on the mass which is currently residing inside the control volume at time t. In some books they write external force, they write R2 as, they don't use the symbol but they talk about the same thing. They write as external force acting on the control volume. I don't agree with that totally. Control volume is an imaginary thing. External force actually is acting on the mass that is real contained inside the control volume. Yeah, that's why I use this set of words here. When the entity is fluid, total energy, kinetic energy plus internal energy. What should be R2? R2 is W dot plus Q dot. I take this much amount of mass. Why would its total energy change? First law of thermodynamics tells me that it will change if there are any of these two things present. What is W dot? W dot is the net rate at which work is being done by all the external forces, net work done by all the external forces on the mass which is currently residing inside the control volume. Units will be joules per second. What is Q dot? Q dot is the rate at which heat is being added, rate at which heat is being added to the mass which is currently residing inside the control volume at this point in time. Okay. This R2 here is a scalar. When the entity's total energy R2 is a scalar, here R2 is a vector and the unit will be newtons. Okay. So the mathematical expression of R2 will depend on what entity it is. We will use the laws of thermodynamics or law of thermodynamics or Euler's axiom to get the mathematical expression. We will derive it in the coming lectures. But for the moment, let's go back to R1. And I want to derive the mathematical expression for R1. The nice thing about R1 is that the expression that we are going to derive, we can derive it in terms of phi, the entity per unit volume. And that form, I mean the full expression of R1 that we will derive, that will be good enough for all entities. Yesterday I was saying that for each of the equations, it requires 5, 10, 15 steps, but the first few steps are common. Those common steps are actually about R1. Let's derive an expression for that. Same control volume I have, and mind you, this is finite size. I have not imposed the restriction that the control volume is infinitesimal or small. It can be as big as you want. Entire room can be a control volume. Okay, so dA is an infinitesimal area on the cross section enclosing the control volume. This is dA on the outer surface. En is the local unit normal pointing away from the surface pointing away from the control surface. In other words, pointing outside of the control volume. This is how I am choosing En to be. V is the velocity vector at x. What is x here? X here is the centroid of that area. And that area is obviously on the surface of the control volume. Okay. Written here. R1 by definition is the net rate at which the entity is pouring into the control volume. Due to what? Due to advective flux. My claim is that the expression for that is simply this, where this double integral means, of course, integration over the surface, and mind you, this is a closed surface because it is the surface of the control volume. This is the rate at which entity is pouring into the control volume per unit time. There is a minus sign here. Why there is a minus sign here? Look at the way I have drawn the direction of En. It is pointing away from the surface. So when you do V dot En, you're talking about a flux. But that flux is in what direction? Out, going out from the control volume, because En is outward normal. But the question I am asking is pouring into the control volume, and that's why I put a minus. Now this expression, you will observe, if you compare, look at the previous lecture notes, this expression is the same that I derived for this kind of hemispherical surface, except for the negative sign. It's the same. It's got to be the same. That surface, the expression that I derived for this surface means the same thing, going from in the En direction, the flux. The only thing I am taking into account is extra, is that it is a control, it's a closed surface, and instead of that plus sign that appeared there, I am putting a minus sign because I have changed the language of the question that I am asking. There it was from side A to side B, and I made the En point from A to B. That's why it was positive. Here I am asking the question pouring into the control volume, but I have taken En in the outward direction, so I have to put a minus sign. Okay. So that is it. R1 is, we have the expression for R1 for all entities. If entity is mass, what would you put phi as? Rho. If entity is momentum, what will you put phi as? Rho times B. If entity is energy, you will put that as rho times V dot V by 2 plus CBT. Okay, good enough to be applied everywhere for all entities. So going back to that equation, the rate at which the total amount of entity is changing into that control volume, there is an advective reason and there is a non-advective reason. Advective reason, I have written it in this way. R2, I will leave it like this because it will depend on the entity, right? Most of the times we take this term R1 on the left hand side. If you want, you can keep it on the right hand side, no problem, but most texts will take it on the left hand side with the plus sign. Starts appearing like this. I want to remind you, N is this. This N tensor is what I have here. This curly V that I have started using since yesterday, mind you, this is the volume. Don't confuse it with velocity. For velocity, I use this. So this integration is over the entire volume. That's why it, please make it sentence. What is N? What is N? Make a short sentence. No. Not flow, no flux. Look at this expression. Okay, first you tell me what are the SI units of N. N, not this. N, यहाँ पूछ रहा हूँ. N का unit क्या है? Not change in entity. No change. N is entity itself. If entity is mass, it is kg. If entity is momentum, it is the total momentum that is residing there, kg meters per second. If entity is energy, this is joule. Now you tell me what this means. Make a short English sentence for me. N. I've told you the SI unit already. Entity is mass, it is kg. So what is N? Amount of mass currently residing inside the control volume. In general, amount of entity currently residing inside the C. Change comes here. In fact, the equation that we are setting up, that equation we are setting up with by trying to find out how it changes. ऐसा यूनिट आ रहा है इसका एंटिटी आएगा पाई का क्या यूनिट एंटिटी पर यूनिट वॉल्यूम दैट इज 5 मैंने dv से मल्टीप्लाई किया at that time itself it becomes entity and then you integrate it over the entire volume. Okay. Fine. So putting this expression also back in here and triple integral, double integral, etc. we have put there. This form or this equation is called the Reynolds transport theorem in fluid mechanics. Now this is going to be the stepping stone for us to derive various governing equations of velocity, temperature, density, etc. We are going to do that now. Now RTT, the way we derived it is true for any sized control volume. And since it is true for any sized control volume, I can try to apply it for a small control volume also, right? Small control volume. That's what I have on the slide. An infinitesimal cuboidal control volume. My working coordinate system is Cartesian, frame fixed Cartesian. This is reference frame F. And I am focusing my attention on a control volume as shown here. It's just like the fluid element. In fact, at this moment, there is a fluid element that lives inside that control volume. At this moment, there is a fluid element that lives inside this control volume. At next time instant, what will happen? At next time instant, my control volume is not going anywhere. Why? Because I have kept it fixed, size, shape, location. But next time instant, the fluid element will, a part of it may move out. Because fluid element is a real thing, it will move. But at this time instant, both are coinciding. Now on that figure, you see I have marked the point Q. What is Q? Q is the centroid of that cuboid. All right. And that Q has the position vector X. In Cartesian coordinate system, it has coordinates x1, x2, and x3. Frame is inertial. I am committing to an inertial reference frame. By the way, I forgot to emphasize it today also. When I was talking about this guidance on R2, and when I said that if it is fluid momentum, You use Euler's first axiom. You can use Euler's first axiom only when F is an inertial reference frame. You are aware of this from APL 100. Same goes for thermodynamics also. W dot plus Q dot equals the rate of change in total energy of a chunk of mass only when the frame is inertial. So if we are going to use this axiom, this law, we have to deal only with an inertial reference frame. So I am committing to that, and we will, if unless specified otherwise, the reference frame is going to be inertial now onwards. All right, the edges of the control volume are E1, E2, E3, just like the fluid element. Control volume is fixed, no motion. Now this control volume, given the shape of it, it has 6 enclosing surfaces, or in other words, I'm saying the control surface that encloses the control volume has 6 parts. Am I right? 6 parts. Okay. Try to recognize those 6 parts by the symbols that I'm going to use. I'm going to use S1, S2, S3, etc. to denote various control surfaces or faces of the control volume. I use this kind of notation or symbol here or diagram, and I think that if you pay attention, it will uniquely tell you what control surface I'm talking about. For example, look at the way I have drawn S1. Even though I'm trying to draw a 3-dimensional figure on 2 dimensions, and things are not very clear, but I hope the way I am drawing S1, it is clear which face I'm talking about. Is it clear? Which face is that? In other words, I'll ask, what is the unit normal to that face S1 in terms of E1, E2, E3? Outward unit normal क्या है S1 का? Plus E1. You're able to see that? On the other hand, observe S2. S2 को देखो कैसे ड्रॉ किया मैंने. Outward unit normal क्या है उसका? Minus E1. Okay. Similarly, one more. Let's check for one more. S4. S4 एक surface दिखा रहा हूँ मैं. उसका outward unit normal क्या लग रहा है देखने में? Minus E2. Okay. So I hope this figure and the way I'm drawing will communicate things. All right. Fine. Identified them on the figure, and Q has coordinates x1, x2, x3. And there is this flow happening. Fluid particles are moving, walls are transparent, some enter, some come out. They do what fluid does, whatever it wants. The control volume is in my mind, is in your mind. There is no control volume actually in the flow. Okay. Now I am going to look at each of the 3 terms in the RTT, in the full form of RTT when the control volume was large. I'm going to look at each of those terms and find approximate expressions for those in context of the small control volume. Okay, so this is my RTT in its full glory, the original form of RTT. There is one triple integral, there is one double integral. Let's focus on this triple integral. My argument is, since my control volume is very small, I can make it as small as I want. This triple integral can be written in this manner. What is this? First, this product is what? What do you guess this is? Volume of the control volume. And what is this value? This value is phi at the centroid of the control volume. Do you think this is a reasonable approximation? Integral of phi over the full volume will be approximately the same as the value of that quantity at the centroid of the volume multiplied by that volume itself, if the volume is very, very small. Fine, we do this kind of approximation all the time. That's what I'm doing here. Now, mind you, some of you might have realized already, some of you might not have. I want to point this out. In its full glory, the full form of RTT applied to a finite size control volume, this phi is at what location inside the integration? This phi is at what location, the way I have written it? किस cube में? You mean dV? Now this is applicable for control volume of any size, right? अब जब any size है तो phi तो vary करेगा, right? Phi can vary with time and space. Time को भी भूल जाते हैं. At any time instant I am talking about. Integration is being performed with respect to space. Huh. So which phi at which location should go in here? Here. Which location? Look at this from simply from mathematical point of view. अगर मैं एक ऐसा इंटीग्रेशन लिखूं f dv, ये f कहां पे? Right, that f is at the centroid of this dv. ऐसे ही तो करते हैं इंटीग्रेशन, right? That projector box is small dv. I will take the value of f at the centroid of that small dv, multiply by that dv. Then I go to another small box. I find the value of f at that centroid of the small box, multiply by that, and usko add kar rahe hain. That's what is happening. All right. So this phi is local centroid of dv pair. Now in this case, what is happening? There is only one small box. So that's why I am taking this value at the centroid of that small box. That's all. This is an assembly of summation or summation of many small boxes. This is just one small box. Similarly, I want to ask this question here, phi and v, there are two variables appearing. Where are they? Again, control, if the control volume is this, the control surface is everywhere, I mean, extended in space. Phi where? Phi where? Centroid of dA. ये surface integral है, volume नहीं है. So there is dA here. dA will have some centroid. dA is always on the surface of the control volume. dA will have its centroid. For example, this panel, and let's take this LED panel. This is my dA. At that centroid I go, I find the value of phi. At that centroid itself, I find the value of v. Right? I do this operation v dot en multiplied by phi, multiplied by the area of this panel, and then I go to the next panel and next panel, add them all together. All right. So here this is at the centroid of dA. Fine. This idea also we will be using to simplify the expression. So coming back to this expression, I hope you accept this approximation. All right. Now let me focus on this. Now, this is the advective flux term with a negative sign. When it becomes plus, I say advective flux with a negative sign. What am I doing in this step? I'm realizing that my control surface in this case has 6 different parts, and I'm going to do this integration in those 6 as in 6 parts. Those 6 parts are written here. These S1, S2 are the same which are marked on the figure. Is it fine? All right. Move on. Then I realized that all the 6 faces that I have their outward unit normals will be either plus E1 minus E1 plus E2 minus E2 plus E3 minus E3. Why? Because I have oriented the control volume in that way. And that is why I am able to bring in some new signs here. Look at this and tell me if it is right. So on S1, the outward unit normal will be E1, as you recognized. So there is, it just remains like this. I mean, En has been replaced by E1 here. But when you go to S2, that En is going to be replaced by minus E1. Here it was plus E1, here it is minus E1, and that's why I have taken a minus sign. For S3 and S4, E2 is relevant. One has plus E2, other has minus E2. And for S5 and S6, plus E3 and minus E3 are the outward unit normal vectors, and thus the whole set has been simplified in this manner. Now V dot E1 so what V here is appearing as vector. I'm going to eventually write this as in my Cartesian coordinate system as this. Okay, so V dot E1 will become V1. V dot E2 will become V2 as far as S3 and S4 is concerned. And S5 and S6, that V dot En is going to give me V3. I am getting specific components of velocity. So that is one change I have done from going from here to here. There are other changes also I have made. What is this expression? What am I essentially achieving here? I am writing a surface integral approximately as product of the area of the face and the value of whatever variable is there where at the centroid of that face. I hope you see that. Mind you, this is not product. The way it is written, it looks like it is 5 times x1. Not. This is argument. Phi at. So this is at. This is also at. Time I have not written, but time is implicit. Everything is at time t. Implicit. Just to save some space. Now please pay attention to what appears in the argument and see if it is making sense. When I am talking about face 1, first I write the area of face 1 or S1. Is this area of S1? It is. And then I need to have the value of 5 and V1 at where? At the centroid of S1. This is centroid of S1. Is this centroid of S1? Am I right in saying? X2, X3 do not change compared to Q. Only X1 along 1 changes, and by how much it changes? By delta X1 by 2. Right? Because Q is at the middle. To go to one face, you travel delta X1 by 2. So that's what I have here and here. So please examine whether others are all right or not. I'll wait for a minute. Please examine all the arguments. Arguments means the within parenthesis what I have. If there is a mistake, please point out. You are not sitting in your right seat today? No, you used to sit there. Yes? Yes. Then yesterday you were not sitting at your right place. Okay, maybe I'm confused. I'm sorry. I felt I saw you there. Well, you are one of the more attention-paying students, so I look at your face, but I am mistaken. Sorry. Please examine. They clear. Please see. So there are two things to be seen here, two things to be paid attention to. That coordinates and the area. There are some changes happening in area also. 2 3 2 3 3 1 3 1 1 2 1 2. That has to be correct. And these things. Does it look fine? Look fine. All right. So surface integral converted to some products. Now let's focus on this quantity, this product that I have on the left right hand side. And here I have changed the notation a little bit because it's getting very wide. I am focusing on the product of phi, the tensor multiplied by V1, where at this location, which is the centroid of face S1, I'm going to write it in this manner. Taylor series. This is actually the full Taylor series right now. What does hot mean? Higher order terms. Is it fine? As usual, when you write Taylor series, all derivatives are at the base location. So all these derivatives which are appearing first, second are at Q. Okay. So now what I'm going to do is to take the first order approximation of this, retaining only terms up to this. So I will not consider this. Maybe I'm doing that later. So right now, I'll truncate the series later. First, what I'm going to do is to replace phi, this product here, and a similar expression which I will get for this. I'm going to replace this and this using Taylor series expansion like what I have shown here, and a similar expression for the other one, and focus on these two terms, dealing with two terms at a time, S1 and S2. The advantage is some terms get cancelled out. That's why I'm focusing on pairs S1 and S2. I have not shown all the steps, but you should do it. Derive it once. So as far as the first product is concerned, I have already written the expression. For the second one, I will need expression when this is minus. Let's do this small exercise. What will change when I make it minus here? What will change on the right hand side? Second term will get minus sign. This will not have any change, and then minus will appear, right? So you can write such expression for both the things and then combine them for S1 and S2 and this is what you will get. So when you combine, take the two surfaces S1 and S2 together, what happens that the leading term, that itself gets cancelled out. The value of phi V1 at the base location also itself gets cancelled out. There will be more cancellation, but the first 0th order term, what we call, that also gets cancelled out. Factor 2 will appear because whatever is being retained, it is the same thing, right? Gets added up. And then there is delta x2, x3 here. Now I am going to retain the first order term of this. By first order term, I mean where it has delta x1. I am going to approximate S1 and S2 contributions in this manner. These terms have all been neglected. I have not written, but this derivative is at x1, x2, x3. Now looking at this expression, looking at this final expression, can we write similar expressions when I take 3 and 4 together? What will happen there? I mean, one way is to, of course, derive it all over again the way we did. The other is to recognize a pattern and write the final expression. And that is absolutely acceptable if I ask you to derive everything. You can derive it for one pair of surfaces and then say that recognizing a pattern, you write the other expressions. So if I change this to S3 and S4, of course, this will change to V2 and this will also change to V2. What will change on the right hand side? Is there a pattern to be recognized? Delta x1, delta x2, delta x3 are all appearing, so it will always be there. What will change? Phi right now is a tensor form. There is no index. It will remain as it is. V1 and x1 are there with indices. What will happen? V2 and x2. You can verify that. That's what is going to happen, and I have the expressions here. When you combine S3 and S4, this is what you will get. V2, x2. And when you combine S5 and S6, you will get V3 and derivative with x3. Delta x2, delta x3 are coming from a different root, but eventually they all assemble and make that product. This product is coming because of the face area. This is coming because of face area in this. Why is this coming? Coming from Taylor series, because there is x2 here. Here this was coming due to face area, and this is coming because of Taylor series. But eventually, as I said, they all become product. So going from one pair to another, it doesn't matter too much as long as you have it on in your expression. All right. So now I am in a position to assemble everything as far as the advective, negative of advective flux term is concerned. This was the exact expression. And with the approximations that I performed for a small sized control volume, this full expression is getting simplified as this. Okay. I don't know what else to explain here. It's mainly algebra. There will come a point when I will also talk about physics, but right now it's mainly algebra. So you have to derive and make sure you understand the derivation process. So now going back to the Reynolds transport theorem, again this is the original form for a finite sized control volume. I have approximated two terms. I have approximated this and I have approximated this for a small control volume. This one, to remind you, the triple integral term was written in this manner, right? And the surface integral term has been written in this manner. Now the triple integral term, which is like this, is eventually subjected to partial with time, right? Now if you subject this whole thing with partial with time, this will simplify to what I have here. I have taken delta x1, delta x2 and delta x3 product outside of the time integration. Why? How can I do that? What is the argument? Very good. Remind yourself, delta x1, delta x2, delta x3 are the dimensions of the control volume, and control volume is fixed. It's not changing its size or shape with time. So when I hit this whole product with partial with time, that simply steps out, stands by. And the real time derivative which matters here is that of the phi tensor. So let's put this back here and let's put this here. Okay, I have something like an equation emerging involving what? Involving phi. Of course, v1, v2, v3 are also there, but the time derivative is with respect to phi. So I will start calling this as an equation of phi very soon. Okay. What has happened to delta x1, delta x2, delta x3? They are common factors. There were common factors for both these things. Both these things, I have taken it on the right hand side. Now I am still carrying this symbol of approximation because Taylor series has been involved so far. But then I argue that as I make this control volume smaller and smaller, this will become more exact. All right. So in that limit, we will write this equation as an exact equation. Partial with time, then some terms involving partial derivative with x1, x2, x3, r2 divided by the volume of the control volume. This equation we call as the differential form of RTT. Differential form of RTT. Take one more minute. Putting the big picture back here. Earlier I derived RTT valid for finite size control volume. I have a differential form of RTT which is valid for small size control volume. Now let's use this quickly before we end this class to find the governing equation of rho density. This is the differential form of RTT. Let me choose the entity to be mass. What will phi become? Rho. What will R2 be for this small control volume when the entity is mass? 0. What do I get? I have the equation of density. This is how density must change following law of conservation of mass in a flow field which is being described using Eulerian description. We'll talk more about it in the next class.